Okay, thanks. And so our last speaker is Yashar Hezaveh, is that correct? Close. And so he also works at the Flatiron Institute, but in a different center. It's called the Center for Computational Astrophysics. And so they're applying computational techniques to study, distant stellar bodies and planets and dark matter. And Yashar got his PhD from McGill University, and then was a postdoctoral fellow at Stanford, and now is a research fellow at Flatiron.
All right. Okay, thank you very much. I'm really excited to be here to talk with you guys about AI, machine learning, and things. So you guys have been talking about that a lot today. But so I'm using that primarily to answer questions about dark matter. And so today, this is the story of dark matter and what we know about it, what we don't know about it, and what we are trying to learn, and how machine learning is helping us for these questions. So our story begins in 1930s when an astronomer at Caltech called Fritz Zwicky did something that nobody else had done before. So Zwicky looked at these clusters of galaxies and to measure how fast individual galaxies were moving around the clusters of galaxies. And so clusters of galaxies are these groups of hundreds to thousands of galaxies that orbit each other. And what's holding them together is gravity. So gravity is the glue that's binding them and holding them together. And so the faster the galaxies they move in a cluster, the more gravity the cluster needs to have to hold them together. And so we can use this, speed of galaxies inside the clusters as a way to measure how massive the clusters are. And so Zwicky did this in 1930s, and to his astonishment, he found that there were about 5 times more mass in the clusters than the amount of mass that he could actually see with his telescopes, in form of stars in the galaxies. So if there weren't enough dark matter in the galaxies, these galaxies, in the cluster, these galaxies would fly apart, and the cluster would never form. And so the conclusion was that clusters of galaxies seemed to have something in them that had a lot of gravity that was acting as this glue holding the galaxies together, but we couldn't see it, and so that's what we call dark matter today. And so a few decades later, Vera Rubin looked at spiral galaxies, like our own galaxy, the Milky Way. And so she measured how fast these spiral galaxies were rotating, how the stars were rotating, and how fast they were rotating in their outskirts. And it was really interesting because she also found out that these galaxies were rotating way too fast in their outskirts. And that could be explained also by the existence of the same amount of matter, like dark matter, as what was implied in these cluster lenses. And so at the time, Vera Rubin's observations were the strongest evidence for the existence of dark matter on galaxy scales. So you kind of see in this plot, so we're just measuring the rotation, and the expectation is that these rotation curves should drop, as it'll be shown in this video in a minute. But the observations indicated that they were rotating way too fast. So ever since then, a lot of different observations have come to the same conclusion, that there seems to be a mysterious form of matter that permeates our universe, and we can find it in galaxies, we can find it in clusters of galaxies, and everywhere else. And we don't see it directly. That's the key point. But we can see its effect, its gravitational effect on everything else, on photons and on regular matter in our universe. And so that's what we call dark matter today. And so the million-dollar question is, what is causing this extra gravity? And so as physicists, we have a few different theories for what dark matter is. But by far, the most compelling and theoretically sound idea is that dark matter should be a form of particle, like electrons, like protons, like neutrons, that has mass. So because of that, it has gravity. But it doesn't shine any light. It doesn't interact with light. So because of that, it's invisible. And so now the race is on to find out what this particle is and what are its fundamental properties and what theory of physics it reveals. What are the fundamental theories of physics, particle physics, that we still don't understand that result in the existence of this missing or exotic particle? So by far, our most accepted and compelling idea for dark matter is something called cold dark matter, and or CDM. I'll refer to it later. And so cold dark matter, basically, cold means that these particles that consist, dark matter is consist of, they don't have much thermal motion. They they don't move around randomly very much at their beginning. So one of the most amazing places where we see the influence of dark matter is on cosmic microwave background, or the CMB. So the CMB is this afterglow of the Big Bang. It's the basically baby image of the universe, only about 300,000 years after the Big Bang. And so satellites like the Planck satellite shown here and other instruments like the South Pole Telescope have measured this distribution, the image of the CMB, and like the image that is shown here. And so this is really, really interesting. This is showing basically the distribution of dark matter in the early universe, because at this time, the universe didn't have any galaxies or stars or planets like it has today. So at this time, the universe was only basically a soup, a cloud of gas and dark matter. And so when we look at the CMB at this time, and when we remove these, this red area that you see is our own galaxy. So we remove our galaxy, then you see these kind of fluctuations that are hot and cold spots. And these hot and cold spots, they correspond to basically overdensity and underdensity, regions. So basically, these are regions where there's more matter and less matter, something like that. And so by looking at the CMB, we can kind of learn about the distribution of dark matter in the early universe, only about 300,000 years after the Big Bang. So that's really exciting. And so once we know how dark matter was distributed at this time, we can use computer simulations to go from that early stage of the universe where nothing really existed except for this uniform cloud of dark matter to the beautiful universe that we have today with stars and planets and galaxies. So what we do is that we distribute dark matter in these simulations, according to the observations that we have from the CMB, and we just let gravity do its job and collapse these dark matter particles to form these filamentary structures that you see here, and so all these overdensities that you see here. So after like billions of years, these simulations, they basically evolved the evolution of structure in the universe and dark matter, and they produce these structures. So where you see these overdensities, these bright regions, these are the places where we have a lot of dark matters collapsing together to form these structures. And that's what we call dark matter halos. So a dark matter halo are these overdense regions in our simulations. So in the 1980s, we also started to have a new theory for the formations of galaxies in a universe filled with dark matter. So these simulations are dark matter only. So there's only dark matter and gravity at them, and inside them. So in the 1980s, we started to have a new theory that said that galaxies form at the heart of these dark matter halos. So wherever you see a dark matter halo, dark matter would kind of pull regular matter, like hydrogen and helium. And at the heart of these dark matter halos, you start to form galaxies and stars. So bigger dark matter halos like this one would form bigger galaxies, and smaller dark matter halos like this one would form smaller galaxies. So what's really exciting about this is that now I can go and compare the distribution of dark matter from these simulations of cold dark matter to the actual observations of galaxies in the universe. And that's really exciting because once we do that, so I forgot to mention this analogy. So basically in that analogy, think about as dark matter as a galaxy as a light bulb. So you have these shiny filament, that's the galaxy, the stars that we actually see, sitting at the heart of an invisible, transparent dark matter halo. And so the light bulb, the glass bulb is basically what's holding the filament in place. So similarly in a galaxy, you have this dark matter halo that is holding, the galaxy in place. But really, the visible part of the galaxy is the filament, is the shiny stars that you see around it. So we can go and compare these numerical simulation, computer simulations of the structure formation in the universe, and look at the statistics of these dark matter halos and compare them, with real observations of galaxies in the universe. And we do really, really detailed comparisons. And it is really astonishing, that we can find extremely good, agreement between the two. So this is a image of the Hubble Deep Field from the Hubble Space Telescope. And so we can compare things like the distances between different galaxies, how they're clustered, and the density, the number density of galaxies across the universe, and a lot of different things. And all of these things seem to almost perfectly agree with each other. And so all these agreements have kind of convinced a lot of astrophysicists that the cold dark matter has to be the correct description. I mean, how else could such a simple model have, predict so many detailed observational constraints that we have. And so at this point, we're all hoping that somebody here on the Earth can detect dark matter, in a lab setting and tell us what its particle properties are and what, theory of physics it's, revealing. And there are many such experiments, one on board the space station, International Space Station called AMS. There's a lot of experiments in, deep mines, abandoned mines like the Lux experiment. But so far, none of these experiments have detected the dark matter yet. And so it's been quite a few decades that we've been searching for dark matter. And so in the absence of a direct detection here on the Earth, us astrophysicists, we're still trying to find out if there is a signal in the sky, if we can learn something new about dark matter, except for the fact that it has gravity, so that we use this information to guide, our search for, the detection of dark matter here on the Earth. So in the early 2000s, as computer simulations, computers became more powerful and computer simulations started to have higher resolution, we started to notice an extraordinary prediction of the cold dark matter model. And that was that the halo of, galaxies like the Milky Way were not smooth, but they were like this. They were composed of tens of thousands of smaller dark matter halos. So, for example, imagine this could be the halo of the Milky Way. Our galaxy with its beautiful spiral arms would be somewhere sitting at the center, but we're expecting that to have thousands of tiny dwarf dark matter halos all around us. And remember that our theory of galaxy formation told us that every dark matter halo formed a galaxy at its core. So if each one of these dark matter halos forms a galaxy at its core, a tiny galaxy, we should expect to find thousands of dwarf galaxies around the Milky Way. And that's where the controversy begins. So after a few decades of very careful search around the Milky Way, we have only found about 50 dwarf satellites around the Milky Way. Thousands of times fewer than the tens of thousands of subhalos that are present in n-body simulations, in numerical simulations of cold dark matter. And so this problem has been called the missing satellites problem. And so what is the solution to this problem? So I'm going to cut to the chase and tell you what could be going on. There are two solutions proposed for this problem. Either these cold dark matter halos, these halos according to the CDM, they exist, we just cannot see them. And the reason for that is that they don't have any stars or galaxies in them. Remember, we're just looking at stars to see, galaxies, but we don't see anything. What if these dark matter halos exist? They're there, but they just don't have any stars in them. If that's the case, it just means that our theory of galaxy formation is wrong. But alternatively, it is possible that they just don't exist at all. And if that's the case, then probably our theory of cold dark matter is wrong, right? So if we could measure the distribution of dark matter on these scales and count up the number of these subhalos, in a careful way, then we can learn, if dark matter is, if this scenario is true or this one. There are alternative dark matter models like warm dark matter that have exactly predictions like the image on the right. So in these models, dark matter has some, thermal temperature, and that temperature basically erases some of the structure. So you can just think about it as the amount of, clumpiness in the distribution of dark matter somehow relates to its temperature. So if we can measure that, we can learn something about the fundamental particle properties of dark matter or its temperature. So I'm just going to do a quick recap of what we talked. So we know that the universe is filled with dark matter. Our favorite model of dark matter is cold dark matter. We think it's a particle. And it makes a lot of predictions for the distribution of galaxies in the universe, many, many different predictions that all seem to perfectly match our observations. So that's really exciting. But when we zoom in on individual galaxies, cold dark matter predicts that the halo of the Milky Way and other galaxies should be extremely clumpy. Now, add to that the fact that we think that our theory of galaxy formation says that every dark matter halo has a tiny galaxy in it. But that doesn't add up to the observations of the Milky Way. We only find about 50 satellite galaxies for the Milky Way. So again, back to the light bulb analogy, you either don't have these light bulbs at all, or you have some light bulbs that just don't have a filament in them. These are the two different scenarios that we would like to distinguish and learn. So the question is, how do we actually find these light bulbs if they don't have any filaments? How can I find these dark matter halos if they don't have any stars in them? So the key question about, the thing about dark matter was that I cannot actually see it because it doesn't emit any light. But we can find it through its gravitational influence on light, or through the lensing effect. So if you just look at, glass balls like this one, you notice that even though they're transparent, they distort the image of background things, and they make it, distorted. They act like a lens, right? So anything that is massive does the same thing. So dark matter halos, they do exactly the same thing too. And that is called gravitational lensing. So, and in particular, something called strong gravitational lensing is the formation of multiple images of a single distant object due to the deflection of its light rays by the gravity of intervening things. So, for example, imagine here we are on the Earth. We're looking in that direction. There's a galaxy. There's a blue galaxy sitting there about 5 billion light years away from us. And then there is a red galaxy sitting right behind the blue galaxy, but much farther away, like 12 billion light years away. And as the light rays of that background galaxy, they pass near the blue galaxy, they get deflected by gravity. So they come to us from different angles. And as a result of that, here on the Earth, when we look out there, we see the blue galaxy, and we see the red galaxy has like arcs around it from different directions, the light rays they come. And it's a little bit like looking at the images of a fish at the corner of a fish tank. I don't know if you've ever noticed, if you look at the corner of a fish tank, you will see two images of the same fish. And the reason is that the light rays, they're getting deflected on the two different sides because of refraction in this case. And so they come to us from two different angles. And if you don't believe me, this is a live demonstration of that with Mr. Mango. So as he goes to the corner, you see the image of the same fish twice. And so that looks easy, but I had to wait a long time to get that. Okay. And that's a real image of a gravitational lens. So here you have this orange galaxy sitting in the middle, and then there's a distant quasar, a single distant quasar that's really far away, behind it, and that quasar is imaged into these two images that you see around it. The two images of the same quasar done by gravitational lensing. So this is another real image of a gravitational lens. So here you have this orange galaxy lensing an image of a distant blue galaxy and forming this arc. But as you can see, unlike the fish tank, it doesn't just produce two images. It produces these like arc-like images, like the one that you see here. And the reason for that is the symmetrical geometry of the lensing structure. Instead of just being like two flat sides in a fish tank, it is kind of spherical. And so you can reproduce images like that at home with a wine glass. What you need is, a wine glass, and, you need a candle for that. And it helps if you've had, a little bit of wine and maybe somebody to drink with. So if you dim the lights now and look through the foot of the wine glass at the candle flame, you'll see that the image of the candle flame wraps around the foot of the wine glass, and it forms these arc-like images, very similar to what you see in these strong gravitational lensing images. So there you go. So this is the wine glass. This is a gravitational lens. So in this analogy, basically, the foot of the wine glass is the lensing structure. And, the candle flame is the background source whose image is being, deflected and coming to us. That was Spark, by the way. He's in Santa Barbara if you would like to visit him. Okay. So when we look at these images of gravitational lenses, there are two questions that we would like to answer. One is, what is the matter distribution in the lensing galaxy? What is the thing that's causing this distortion? And so think about it as the shape of the wine glass, right? If you know the shape of the wine glass, then you know how the images are getting distorted, no matter what the images are. And then the second question is, what is the background? So what does the background source really look like, right? So if the candle, has been distorted into that ring, I want to know what does it really look like undistorted. So if I know these two things, I'm done. I have figured everything out about this system. And so to see that, that these two completely define a system, just think about simulating a lens. So if you gave me an image of a candle and a wine glass and you said, well, produce a lensed image, of this thing, what I'm going to do is I'm going to get the wine glass first, and I'm going to do a ray tracing simulation. Basically, I'm just going to calculate at every point how a ray of light is going to get distorted. So what comes out of that is basically a vector field, a distortion field that says every pixel moves according to some direction. And then what I do is that I put the image of the candle in that vector field, and I say, well, that pixel has to move from here to here to here, and I'm going to make that distortion, and I get a lensed image. So that's pretty easy. Producing a simulation of a lens system is very easy. But when we have real data, it's kind of more complicated, because I neither know what the background source looks like, nor what the lensing is. right? And the problem is that I don't know the inverse of this function. I know how to simulate forward, but once I have it, I don't know, it could be that candle and a different wine glass or whatever it is. So how do we solve this? So we solve this by something called lens modeling, or maximum likelihood lens modeling, where I'm just going to try to simulate a lot of lenses and compare them against the observation and hope that if it really looks like my observation, I declare that I found the correct parameters. So if I just try this, experiment for every possible candle and every possible, wine glass that I have and produce like a gajillion simulations, and I compare all the simulations to my real data and say, well, these ones are the ones that are very close to the data, then I can say, well, the background source must look like that, and the wine glass looks like that. And so this is called maximum likelihood lens modeling, because to compare these observations to the simulated data, you use this likelihood function, which, basically, the likelihood function that you try to maximize. So this works fine, except that you can imagine I need to run a gajillion simulation every time that I need to do this comparison. For every new data set that I have, I need to run gajillion simulations to figure out what, kind of like parameters here match my data set. And that might work fine now because we only have a few hundred gravitational lenses altogether. So right now we only know of about a few hundred gravitational lenses. But in the next few years, with surveys like LSST and Euclid, we're expecting to discover about 200,000 new gravitational lenses. So 1,000 times more than the current number of lenses that we have. Now, if you assume that the analysis of a single lens typically would take something between a few days to a few months, depending on the complexity of the system, and during that time, you usually require somebody to sit at the computer and run these, modeling codes all the time. So if you just extrapolate that to the 200,000 lenses that we're expecting to discover, you need something about 1,400 human years or 100 people working for 14 years to produce just like very simple lens models for these LSSC lenses. And so that's like clearly not feasible. So what we have been trying to do is just to say, hey, this is a function, or at least I think it's a function. Can I put this inverse function, can I produce this inverse function with machine learning, with neural networks? So I know that neural networks are excellent function approximators. So can I kind of build that function? And if I do that, then I can just like put my image through this like neural network, and as a result, just get my answers out without needing to produce so many simulations every time that I want to get the answers. And to do that, we went to something called convolutional neural networks. So these are designed specifically for image analysis, and mostly they're used for classification. So the neural network would look at an image of a bird or a cat or a dog, and it would classify it as different categories. And a few years ago, people started to use this for lens finding. So they would train them in a supervised way to find lenses. So they would look at this image and say, that looks like there's gravitational lensing going on. That's a background source to be in lens. This one doesn't look like it. So they would find gravitational lenses with this. But what we wanted them to do was a little bit different, right? So we wanted to actually measure a property of the images rather than just classifying it as something like that. So I want you to look at an image of a dog and measure, for example, its height, its weight, predict its age. And so specifically for our lensing scenarios, we wanted to feed these images of gravitational lenses, directly to neural networks. And as their outputs predict, things about like the mass of the galaxy, the orientation of the lensing galaxy, how clumpy it is, and all sorts of questions about, or the image of the background source. So what do we need to do that? As you can imagine, you need a large training data set. And as I mentioned, we only have a few hundred gravitational lenses altogether. But as I also mentioned, it's very easy and very cheap to produce simulations of lenses. So what we did is that we produced a simulated synthetic data set for training. So what we did was we got these unlensed images of galaxies, we put them through simulations, and we lensed them, and we added all sorts of effects like the blurring of the galaxy of the telescope optics, various forms of noise, various forms of distortions like cosmic rays hitting pixels, sometimes pixels malfunction and things like that. And so we produced a huge data set. We produced 500,000 simulated images, and we trained multiple neural networks, including Inception, which was this very deep network designed by Google. And once we trained them, and training, so I have to say, training typically took about 1-2 days. And so once we trained them, we tested their performance on 2 data sets, about 10,000 simulated images from the same pipeline that had generated the training set, and 9 real images from the Hubble Space Telescope of lenses. So these are 9 gravitational lens background sources that from the Hubble data. And these were kind of the results. So these were the predictions of the networks as a function of their true values. And for the real data, the true values were taken from previous published works. So we could have really, really good approximations of these parameters of the lensing, except that it was like 10 million times faster. So instead of weeks of analysis for a single lens, I can just stick it into my neural net, and in 1/100th of a second on a single GPU, I would just get the answer done. And so the 1400-year analysis of LSST data, it could be done in half an hour on a single on your laptop, right? So this is like phenomenal gains in speed for us. So that's been really, really exciting. So we did this work about a couple of years ago, and ever since then we have kind of been expanding it. We've written a few different papers trying to expand this and apply it to various questions in strong lensing studies. So one of the things that we've been doing is that can we actually, once we figure out these distortions, can we actually have the neural networks correct for the distortion effect? So the networks would get these lensed images of background sources and correct for the distortion and produce an unlensed image of the background source like you see here. So in this case, this is the prediction of the neural network, and you can compare it with the truth. So this is the truth. We know in this case, because these are control experiments, these are simulations, so we know what the truth is. And so they did really, really well, and that's really exciting. And so back to the finding subhalo problem that I mentioned. So we talked all about this dark matter subhalo. So where are we going with that? So this is really ongoing work. But so think about these dark matter subhalos are just like a water droplet on the foot of the wine glass. So we talked about the analogy of the wine glass is the lens, but the wine glass is the massive galaxy that's doing the lensing. These tiny dark matter subhalos that we want to find, they're really like tiny water droplets on top of the foot of the wine glass. So they do a tiny distortion to the image of the background source that allows us to find them, but it's a very, very subtle distortion. And so a few years ago, we did the analysis of this gravitational lens. So you see these beautiful arcs of the background source being lensed by this blue galaxy. And after 2 billion CPU hours and a year of analysis, we found this dark matter subhalo at this location. So at this location, so we found, a very strong evidence for the existence of a subhalo at this location by very careful analysis of these distortions in the images. And so this was a video that I made at this point to kind of show the effect. So basically, you have this background source, red source. If you put the galaxy right in front of it, you do the lensing. So you see these beautiful arcs forming. And if you had a tiny dark matter subhalo at that location, it's going to cause a tiny kink in the images. So you'll see it in a minute. So you can see as that background source comes in and out, you see the tiny kink in the images. So that's a tiny signal that we're looking for. And in fact, this signal here is a little bit exaggerated. It is much more subtle and is weaker than this. So back to the neural network. So what we are trying to do now is actually get these lensed images of background sources and go straight from there to the very detailed distribution of mass, including the subhalos in the lensing galaxy. So our networks are getting these images that have the images of background sources and are taking us to a map, to an image of what matter distribution looks like in the lensing galaxies. And so this is one example of such, this actual work. So this is the lens images of the background source. There are 3 galaxies doing the lensing, so it's a complicated thing, and this is the prediction of the neural networks. So this is really, really exciting. And if I have time, after the talk, I can show you, more examples. So I started by talking about clusters, and I want to kind of finish by talking about clusters by showing you an image of this beautiful cluster. So this is an actual, Hubble Space Telescope image of a cluster. You have these hundreds of galaxies kind of clumping together, and with their total mass, they're kind of distorting the images of background sources and causing these arcs. All these arcs are strongly lensed background sources, background galaxies. It's amazing. It's absolutely amazing to look at these things, to look at these arcs. And the complexity of the system is crazy, right? So how are we, so far, with traditional lens modeling methods, we still cannot really figure out what are the mass distributions in an accurate way. So we're hoping that with machine learning, we can really tackle these extremely complex systems in the future to figure out, what is the distribution of dark matter on these scales and the complexity to be able to answer some key questions about dark matter. All right, thank you very much.
Okay, thanks a lot, Yashar. Some questions?
So this may be an obvious question, but were any of the lensing or data that you looked at from galaxies that you couldn't visually see? In other words, was there any evidence that that was dark matter that was doing it?
Oh, okay. So, are you talking about the main lens? Did you see beautiful arcs and nothing in the middle?
Either the big main lens or the sub piece.
Yeah. So the big lenses, you will never come across something that has beautiful big arcs, because that requires, let's say, 10 to the 12 solar masses, so 100 billion solar masses, 1,000 billion solar masses. And on those scales, we know there's a lot of dark matter, but there's also a lot of stars. It is kind of because they form together. You don't have if there's a 1,000 billion solar mass halo, it will suck in baryons, regular matter, and it will form stars. The question is that on the very low end, when you start having a million solar mass subhalo, the idea is that these are so weak, the gravitational potential of these tiny subhalos is so weak that it might not be able to keep its baryons. So you would have a supernova explode, and all the gas in the halo would just go out. And so on those scales, that's the place where we don't know. So we never see massive arcs forming around nothing. On the lower side, there have been some cases where you have actually visible satellites. So you would see the lensing, and you would see a visible satellite. So you can use it to measure its total mass. You can also look at how much stars you see in that, and you can take the difference, and that would be basically your dark matter. But the detection that we had, these are kind of pushed into the regime where we don't see any stars. Now, we don't see any stars. It doesn't mean that there's 0 stars. It means that there's just few, such that they're below our detection thresholds. Yeah.
This may sound like an incredibly stupid question. I hope not.
I think there's only stupid answers, no stupid questions.
We'll see. I think it was last year that we saw the LIGO speech here at this same conference about gravity waves. And it seemed to me at the time that a gravity wave detector, a telescope that detects gravity waves, might provide some interesting insight about the universe. Is there any talk about such things? Are there efforts to design such things? And how would that apply to a search for dark matter halos?
So the detection of gravity waves has happened, so it's really exciting. Mostly, the detection of gravity waves is just supermassive black holes or neutron stars, orbiting each other, merging, and giving off some radiation. So there are some non-standard theories saying that some of these could be dark matter. So you can have something called primordial, I guess that's not even dark matter. So it does relate to dark matter. So there are theories saying that dark matter is not these particles that we think it is, but it's composed of some primordial black holes. These are black holes that formed at the very, very early universe. And so there are theories saying, well, if there are all these tiny black holes, all across the universe, they could also merge, so they could be responsible for part of the signal from gravity waves and things like that. But that is kind of I was saying, that's not the standard, kind of narrative in astrophysics. So gravity wave is kind of answering kind of different kinds of questions. It's answering what is the fundamental behavior of gravity in these extreme regimes, and kind of giving us a lot of astrophysical information for how supermassive black holes form. And so it's kind of different questions. And things that we are trying to address here is really fundamental nature of dark matter, that doesn't really interact that much. Dark matter never comes up that much to form like, black holes, but we're just trying to kind of like map it out in the universe to learn something new about it.
The pictures you were showing with the arc made sense to me, but you showed one with the quasar that wasn't arced. It had just two images left and right. What was the deal there?
Yeah. So the theory of strong lensing in general, it goes like this. So if you don't have any lensing happening just like that, you have one image. And when you have these like distortions of space-time, every time that you make a distortion, you add two images together at the same time. So in reality, you go, once you kind of start like, pushing, so think about it. So if I just like have one, point and I put a lens in front of it, there are two light rays that go from the two sides that they come to you. So they make two new images. But there's also a light ray that goes right through and that comes to you. And so you have three images. Usually that third image, the middle one, is so dim that we never see it. But then you can kind of like basically bend this one more time, and every time you kind of like bend this like geometry of space-time, you add two more images. So you can go from like 3 images to 4 images to 6 images, well, plus 1 every time. And so the one that you saw is in something what we call double lensing image. So when you have doubly lensed something, you're kind of in this regime where the geometry is such that you just get like the two. So even with a wine glass, you can like play at home. So if you just kind of like put the candle and you rotate the wine glass so that it's more like spherical, and you look at it in some angles, I think maybe even in the video that I had, you could see it. You would only get 2 images. And if I go back to the wine glass here.
So point source versus...
Yeah, and also point source. So oh, that's Spark coming back. Well, we don't have to see all of this again. Spark, do your job. Okay. So just look at the different geometries. So at first you see one image and then another one on top, and then sometimes you see these extended arcs. And so something that my friend Lars just alluded to is that when the background source is extended, it's not just a tiny point source like a star. There is like every point of that background source kind of like illuminates a different part of this image. So that's when you start getting these kind of ring-like structures and extended structures, because there are like every point in the background source is kind of like mapped to like 2 images, but there's like many different points in the background source that are illuminated by the candle, because the candle has some finite extent. So you get these kind of like, funky geometries.
Some kind of alignment as well, right? The alignment of the dark matter halo.
Sure.
Is it spherical or not?
Yeah.
But actually, my question was, those beautiful animations you showed in the beginning are some better than I've ever seen. Do you have? Are you going to let us look at those or use them with our students?
Oh, sure, absolutely.
We would love.
Yeah.
I think that would be fantastic to share them.
Yeah, absolutely. Some of these, I've made them a lot of the lensing ones are, I made all of them. Some of the cluster one going around, that's from the dark universe. Okay. And so that was made by, I think, Ralph Kaler at Stanford. Okay. And, but yeah, I think, we upload the talks online, right? Yeah.
So, and also our contact information is in the yellow paper as well in the folder.
I had another question though about the how does cold dark matter and warm dark matter differ? Is there an assumption on their interaction?
Yeah.
And then how does warm dark matter work? Because if it's warm and it has a temperature, I don't understand.
Yeah, great question. So I'm gonna go and open a different talk, and let's go to. I'm sure I put that somewhere in this talk. Yeah. So okay. So think that everything that happens between cold dark matter and warm dark matter happens in the very early universe. Like today, dark matter is cold no matter what. And by cold, we mean that today, it doesn't have thermal motion. The reason for that is that the universe has been expanding so much, and that expanding of the universe cools things down. So the question is, was dark matter warm at a very critical point in the early universe when it kind of decoupled from regular matter? So think that in the early universe, very, very, very early universe, you had two kinds of density fluctuations in the universe. One like this with long, wavelengths like this one, and another one with a kind of a, shorter wavelength like this one. And so we have a kind of a superposition of the two modes, which must look like this. So just think about this, that this basic image is representing density of dark matter in the very early universe. Now, in reality, each one of these kind of blobs is just represented density. You can have a realization of this. So you could have something like that, where every point now is a dark matter particle. So these dark matter particles, as you can see, there's structures. So there's like these like high frequency modes that you have, and you have these like low frequency modes that you have here, right? So now think that these dark matter particles had some thermal random motion. They could just like move around, randomly. If they did that in a limited amount of time, if they moved more than the wavelength of the smaller mode, they're going to erase that structure. But on larger scales, the distribution remains kind of unchanged. Right? So, and that is why cold dark matter and warm dark matter, so this is cold dark matter, this one is warm dark matter, they have the same predictions for the distribution of matter in the universe on large scales. That's why, warm dark matter is also a perfectly good fit for, clusters and, intercluster, larger than cluster cosmic scales. But on smaller scales, those tiny fluctuations have been erased. And so, structure on those scales never really forms because of those thermal random motions. Now, why does that happen? There's like different kind of competing theories, depending, if you go to like particle physics, and there are theories that, from axions and this and that would say why a particular particle, from a theoretical perspective, would have that temperature at that point. And that's what we were trying to answer here. If we can measure that, can we kind of rule out some of these dark matter models and kind of learn which one is kind of a good candidate?
Since you have lenses and you have light and you have images, can you take your algorithms or something similar to take a picture or an image from, say, the Keck telescope and Mars and machine learn to get better resolution?
So use Mars as a lens?
No, just take the image that you would get from Keck.
Okay.
And go do a satellite that's going around Mars.
Right.
And then take those images and make the Keck image learn to make the image that you would get from a satellite.
So is any lensing happening? There's no lensing happening?
Well, couldn't you use the same idea?
To increase your resolution of your images? So that you could do that. So this is kind of like an active thing in machine learning called super resolution. So you would get kind of a blurry image and predict, kind of like have a higher resolution version of that. It is similar to something that we have done here. I'm not going to talk about that, but basically when it comes to super resolution, the key point here is that you don't really have information, right? If I get an image of this room and I just blur everything together and I give you the new image, I have kind of erased a lot of information in that region. Like that information has been kind of like, it's not about how do I get it out, it's just gone. So in all sorts of super resolution things, the question is that, can you learn a prior? Can you guess what's under it kind of like in a better way than somebody else? So if I get a blurry image, I might just go by hand and paint the faces on top of it because that's my prior information. So there's a lot of machine learning and neural network works that are trying to do that, and they do fantastic jobs at it. But yeah, so sure, yes.
Okay. One of the things that kept on coming to mind was an Einstein cross.
Yeah.
So my question is, what's the difference between the systems that reveal an Einstein cross compared to those that reveal the beautiful arc?
So it's exactly the point that Lars alluded to. So if you have...
Because you were kind of going towards it when you were talking to him, when you said anything that comes in, you have the split, you have two different...
Yeah. So what happens is, I'll try to... I don't know if anybody can see if I draw on the board here. So if I...
I guess the question is why 4 versus the continuum?
Yeah, I understand. So what happens is that something called caustics. So caustics, and you can see caustics. So I really encourage you, go home one day, get a wine glass, and put it in sunshine. Have a sip, and then, so what you do is that you get your wine glass. So you have the foot of the wine glass, and you put it, in sunshine. And the reason for that is that sun rays are just like, so it's parallel, so they will hit this, and put it at an angle. So you put these sun rays that come at an angle, and they go through this, and what happens is that when they come out, and just put a piece of paper under it, and you will see that they form a little, diamond like that. Yeah, the diamond shape. So this diamond shape is something we call a caustic. And so what happens is that, in this case, anything that goes in the caustic, you can imagine, anything that was on the caustic, it gets super magnified. So when you have a lens and you put something at its focal point, and so if you put a light at the focal point of a lens, it comes out in parallel. So these caustics are really the focal points of this lens. So anything that I put on these caustic at different points, it kind of gets magnified with a huge, huge factor, theoretically infinite, magnification. But it gets points, so things that are on this caustic, each one of them, or things that are inside the caustic, each one of them gets mapped to 4 different images. So if I put a source that's inside here, the light rays, I use a sun ray in a reverse mode, right? So in reality, we're thinking about the light rays going from here to outside, but to see the caustic, you put the sunshine and it goes through. So a point that's inside the caustic gets mapped to like 4 different images, and that's your Einstein crossing that you mentioned. But if I had a source that was big, it's not only like a kind of a star here, it's like it's an extended source that illuminates all of that region. So there's another part of that source that gets mapped to another like 4 images. There's another point that and so that kind of causes some continuous kind of ring around it. Yeah.
All the more reason to drink wine today.
We have time for 2 last questions.
If I was talking to some young minds here, and they asked me what is dark matter, can you take it from there?
What?
High school kid.
High school kids.
High school kid, yes.
It's what gives me a job.
So you could...
I would say that dark matter is a mysterious form of matter that we don't know what it is, but we know that it's there because it has gravity and it pulls on other things. And this is not a new idea in astrophysics. In the past, we have seen things like that, like the discovery of, I think it was Neptune or Uranus, I don't know which one of these planets. Was it Uranus? Was discovered in a similar way, where people looked at the orbits of other planets around the Milky Way, around the Sun, and they realized something is wrong gravitationally, and so there must be something going on, but they didn't know what it was. And then later they went and they hunted for it, and they're like, oh, there is a planet there. So in the case of dark matter now, we've done that search, and we think if it was anything there that reacted with light, we would know that it's there. So that's what makes it kind of mysterious in that sense.
This may be kind of a dumb question, but can dark matter and normal matter coexist in the same place in space?
So the theory of dark matter would be, yes. So basically the idea with dark matter is that it is so not interacting that it just goes through regular matter. So if dark matter particles exist according to what we think, there's like a gajillion dark matter particles right now going through your body, going through my body, just like neutrinos. And they just don't interact with regular matter because interaction with regular matter mostly happens through, electromagnetic force, and so, it gets, once you get to the quantum regime, we don't have a theory for dark matter really because we don't know what it is. But in principle, it just goes right through regular matter without interaction.
Will their gravitational magnitude, or like the amount of gravity that they have, kind of add, like the normal matter and the dark matter at the same point?
Yeah, absolutely. So maybe, a good way for me to lose weight is just to get rid of my dark matter. And, but, so it's true. So dark matter has gravity. In theory, it has gravity here on the Earth. The problem is that on the Earth, in these settings, it is so diluted. There's so little dark matter, compared to regular matter. So the density of dark matter in the universe, any point that you get, is extremely low compared to here. Because here on the Earth, we're somewhere where everything is so piled up together and so dense, so there's a lot of gravity. Dark matter is really not dense. But so the question is, why is it that we say it's 5 times more than regular matter? And the reason is that, the universe has a lot of volume. So there's all these volumes. You have to add up the effect of the volume, where you have tiny bit of dark matter in every, cubic meter. But once you kind of like add up over billions of, light years, that amount is really huge because there are regions in the universe where there's a lot of dark matter and not enough, regular matter as, high density as we have here.
Does it have inertia?
Anything that has mass has inertia, yes.
How much of a fudge factor did you have to assign to dark matter in order to make the math work out for the galaxy rotation? Is that like a 0.002 fudge factor? Excuse me if I use fudge factor.
No, okay, yeah. For the galaxy rotation, So for the galaxy rotations, so the question is that, so you see that these stars are moving really fast. They're rotating super fast. So now I will just get the stars that I see in the galaxy, and I say, this is all the matter that I see. And could it explain these like super fast rotations? And the answer is definitively no. Like there's no way I can fudge anything here to just say, there's only one thing you could do, and I didn't talk about that, and that is to change gravity. So if I just say, well, I just changed my theory of gravity from general relativity and what Einstein said and whatever to something else, maybe I can start to fudge it around, just say regular matter can explain that. But that is not the conventional or standard way to do this. So if you assume that regular matter has, standard gravity as we know, and you just try to see it, there's no way you can explain it. Now you can go to dark matter simulations, get what you get out of that, and compare them against these, rotation curves. Now there, I'm not an expert of that, so I don't know how much fudge factor you need there to kind of translate from these simulations to these things. But generally, that there's agreement there.
If I could just have one last follow-up. So,
sure.
What you're describing are we used to talk about machos and wimps. So what I'm hearing from you is that the wimps have won out and the machos are not really what people think are responsible for dark matter?
Yeah, so people looked at machos by similar idea of strong lensing, except that it was microlens. So the idea was that if you have these machos, in the halo, so we would look at kind of like nearby galaxies, and if there's a lot of these machos, they would kind of cause these kind of brightening of the background sources.
And we should point out machos, massive compact halo objects.
Yeah, so macho is basically an alternative, theory for dark matter that is not particles, but it's kind of like more massive things. Think about it as, massive planets or, brown stars or things like that. And so machos have been mostly ruled out. WIMPs are only a class of, particle dark matter. So WIMPs are also starting to have trouble explaining because there's a lot of direct detection experiments that are ruling out, more and more the parameter space of the WIMPs. And
which are weakly interactive massive particles.
Yeah, so weakly interacting. So of all sorts of particles that, theories that we have for particle dark matter, WIMPs are basically a class of them. And we'll see where they go. Thank you.
So I hate to quench the discussion, a lot of questions, but the shuttle is here, I believe, and we have some announcements. But let's thank all the speakers for today before we close.
All right, thank you.
Thank you for all the great questions and your attention and your time.
So let's thank Miles as well for all of his hard work at pulling this together. And we can announce next year's Teachers Conference will be Saturday, January 18th. I'm looking at Maggie because she's confirming I didn't screw it up. The topic will be quantum gravity. So for those of you who like quantum mechanics and gravity, just can't get enough. But most importantly, we really want you to spread the word. It's great that many of you return, and we can always do our best to accommodate you, but we want to see this room full, and I want to next year ask the same question and again have more than half the people raise their hand that it's their first time. So thanks to all of you for coming, and I think the shuttle will start heading out. See you next year for some of you. Yeah, right where you dropped them off.